So let's move to this slide for the graph model. Okay, I skip this. We already know. Oops. Okay, for the graph model, I think this is one of the very interesting structure. Okay, data model, NoSQL model. Oh, sorry, I have not shared yet. Okay, here is the slide for the graph model. Okay, we start from here. And I skip this recap because it is pretty clear already. And then in terms of a graph, it is one of the data structure that I believe you learn in even your undergraduate course on data structure and algorithm, or your master course on the same subject, or even you have not learned in any previous courses before. It is also one of the very straightforward structure and model that you can easily understand. With the graph structure, basically the basic elements within any kind of graph data structure, it includes a first node. Node could mean any of these symbols, right? Here, this is a node. This is also a node. This is also another node on this example. And then another structure apart from node is what we call relationship or link. Link means a relation that two nodes could have with each other. Basically, a link can only relate two nodes, right, at a time. One link. So it comprises basically nodes and links. But of course, there are also different ways to call it. Sometimes, of course, here, either it is a link or relationship between nodes. Sometimes it may call edge. Okay. And apart from just nodes and links or edges, there could be also properties, details to represent, to store data related to the node, related to the link. And the link itself could be directional or not direct, bidirectional or unidirectional. Okay. It depends. So you need to define properly for your structure whether the link encapsulates or represents unidirectional or bidirectional. If it has direction, you really clearly need arrow, right, to tell that the link has which direction. And a query as well as operation on a graph basically are based on graph traversal algorithm, in which you are traversing on the graph. And the very biggest advantage of a graph model is that it's very intuitive. This is a very easy, I mean, to me, I found this is the very easy structure for you to understand from the visual representation. That is one of the biggest advantage. The understanding, the semantic that carries on the graph structure itself, it has very straightforward ways to represent the relationship, the node, and the data. And also, in terms of the graph operation, it requires no join. When we already, you have been working and completed already the RDB project, you soon will finish your document project. You could see that it would require you to do join because you have data on separate collection or table and so on, right? That you cannot deny to join data. But in graph, it's just traversing, following the link, and there is no such operation of joining. Okay, let's look at some examples. So you can use graph model to represent various types of data in which node could represent object entity. And most of the case, we normally label our node, right? So that you can give some meaning or give some labeling to it, okay? And you can even give some kind of entity type or node type as well. So actually, for example, this is a graph. It could be that you have this first node. It is labeled with person. So this to say that this node belongs to the type person, object person, and the node can have name value pair to represent properties associated with the node as well. And of course, in this example, first property is name with the value Dan. Second property is born with the value this day. Another property is the Twitter with the account, right? Another node here, of course, the same type person. Again, NoSQL model, whether you have very strict node schema or not, that is also fine. So this node has name, has born properties with specific values associated with it. And another node of the type car with certain property and value, brand and model. Okay. So these are nodes. Then we could have link, right? Or relationship. And you could see it has direction. In many cases, the relationship is more or less having unique direction. So you need to specify. For example, it is the relationship drive. So it should be that a node person drives a node car, right? And another example of the relationship as well. And another. Okay. And the relationship may also carry property, value, property name and value pair. Some may not. Yes. Again, please, sorry. Okay, if you want to replace by this, yes, that is fine. Yes, it would be fine. But sometimes the unique direction would carry different properties. Yeah, of with the relationship. So it would be mostly separated, but of course that is possible too. Okay, anything else I should say? And I think this is more or less very, as I said, very straightforward. Okay, you can use node link to represent any kind of data you may want to easily. For example, if you think of your own mini project you are working on, right? There are, for example, if we are thinking of just simple things like e-commerce related stuff, of course you have the node. For a customer, this is supposed to be the type of the node, right? But the customer could have certain customer ID with some value, customer name with some value, and so on. A customer may have made a purchase order. Your order, of course, should have the order ID, order date, and order amount. I mean, total amount of the order, and so on. And many more, right? Of course, your order may consist of many of the product items, product lines. Of course, the order may consist of this product for quantity. Two, maybe it's about a notebook. Maybe HP something. Oh, sorry, must be product ID, right? Product ID HP123 and so on. And this order comprised of this product for 2 units and comprised of other products and so on, right? And even if we look at this example, this product item, of course, it may be consisted in many other products too. If we just model the product, right? The product type and so on. So there could be many orders that comprise this kind of product and so on. Okay. So this is one example, one simple example, but to find in a more detailed way, of course, it will require more, but the graph could become very big. That is one of the disadvantages. The size of the graph will become big to visualize, and of course, you may need very good visualization tools to browse your entire graph. But more or less, if you follow one graph, one link, one node at a time, that is very easy. Okay. And what we will be practicing in the lab that you will be using, but there are many other graph store as well, is what is called, what we will be using is called Neo4j. It's one of the top store engine for graph model as well. And it has as its own the query language, but it's become one of the I can say de facto standard as well. Okay, it is very wide because of the widely use of the engine itself, and the query language is kind of easy to understand. It is kind of SQL-like language. And making use of patterns for the traversal, for the relationship of node and link and another node. And it is a way which is declarative and self-describing. You will learn this in more detail from the lab. But what could be seen from here is that actually this is the very visualization of a graph, right? A graph visualization. But if you serialize the graph visualization into textual representation, there are certain syntax that you may need to learn and follow a little bit in the Cypher query language. For example, we need to specify the type of the node you are looking for or interested in. You may need to define the property and value pair to filter which particular patterns in the graph you are interested in. Okay, for example, suppose we are interested in any person node whose name is Dan. We just do this. Of course, there can be many nodes with the name Dan who are, I mean, this is not a unique name, right? Could be many people share the same name. And we might be interested in another person node whose name is Anne. And these two nodes have relationships with the label love. So this is a clause that represents this pattern. And this is a part of the graph pattern that we can express using Cypher. Okay. So as I said, basically, we do all the operations, the query by making graph pattern. So the query execution mechanism of graph, if it follows the pattern, graph pattern execution mechanism, we will just define the patterns we are looking for. Okay, and we'll try to find from the entire graph structure which part within the entire graph database match with the pattern you define. Okay. So this could be an example way. This is the pattern we are defining. Okay. This is just a query clause. We want to say that we find any person node whose name is Andreas. That's it. If there are more, it will identify that those nodes for us. If there are more than one single node in the graph, okay. And in this case, we are trying to find from this example, first finding a person, right, with the name Andreas as a starting point. Then we say that follow a relationship from this starting point that we could identify, follow with the relationship friend. So if this is the relationship friend, we will follow. If this is also relationship friend, we will follow. Okay. If this is a relationship friend, we will also follow. And this is a kind of variable. So we will make following relationship friend to another friend, to a variable friend, and then that variable friend must have another friend too. So we are kind of finding friend of a friend. Okay, friend of a friend of Andreas. That's it. That is why we would return this and maybe this and this and this as indicated, because if you try to follow the link, you will see that this is also a friend of this friend. This is a friend of this friend, a friend of this friend, and so on. Okay. So this is just an example, but you will do something like this in the lab. And it is some way to make it easy to follow. Just make a graph pattern and what you want to traverse. So it's like you walk through the graph. Okay. And so on. Okay. This is another query. Whom does Anne love? Of course, if you convert this into the query expression in Cypher, should be, of course, first we find a person and the person node and then follow the relationship love and by the node that and love with whom, and then return whom as the answer. So who will be the node? That is the person and love, and so on. Okay. And what does this one do? Can you look at this for 1 minute and tell me what does it do? Maybe you can type in the chat or speak it out. Yeah, what is return? Maybe you just answer what is return, right? From here, of course, it returns B and C. But what are those nodes, B and those nodes, C? Emil and Ian. Emil is B or Emil is C? Be specific. Yes. Others from the online? Yes, let's have a look as well. Yes. I think this is pretty straightforward, right? First, Jim, where is it? Jim knows B. So actually the person Jim knows could be both Ian and Emil. These are candidates for B, but B must also know C. If we get Emil as the B, Emil doesn't know anybody else. So Emil does not satisfy this condition or filtering condition. So we cannot have Emil for B. But then Ian knows Emil. So Emil can be C from Ian, and so on. Okay. If actually there is this, then there will be two pairs, right, for the answer. B for Ian and C for Emil, and then B for Emil and C for Ian. You will get two answers if I modify the graph like that. Oh, A must know C too. Yes, exactly. And that is fine. Okay, for this case. Yes. Yes, exactly. So we use the graph pattern to write the query. The thing you have is that you need to write to perhaps draw some graph patterns that you think it would represent the query, the data that you need, and write it that way. So the very good thing, okay, we talk about the pain of DB relational model first, right? Complex to model and store relationships when it is very relationship intense data, intensive, relationship intensive data. When your data consists of huge relationships, relational model may have certain limitations because it requires a lot of foreign keys. Try to think of modeling data in relational model. With a lot of relationships mean that you have a node could be one table. Relationship from one node to another means foreign key between the two tables, right? The record within these two tables. Then the relationship by means of foreign key is fine. But then querying with foreign key among tables would mean joins. And joins are the very expensive operations in relational model. Okay. That is this big limitation. Queries can be long and complex if you have a lot of joins. Maintenance to make sure data consistency is there, it will be very complicated. This is very usual way to model. Let me move this. Very usual way to model sell, buying, purchase order, right? You have user or customer, you have order item, line item, and product. Fine, this is very usual. And this is very similar to what I already discussed. If it is table, it will be like this. This is table user. Each of these is one row, of course. Each of these is one row for order, one row for line item. I mean the table, product, line item, order, and user, like this. And each represent a single row. And when you have relationships among these tables, right? This is user Alice. What does she buy? If we want to analyze what are the items Alice has been bought along her lifetime being our customer, of course, you would be able to browse and find that these are the order records that belong to Alice, right? Look at the arrow carefully too. This arrow refers to foreign key. Foreign key start from the order back to Alice, right? Okay. So we want to find the order that belongs to Alice. We want to find the order item from each of these order as well. Okay. So this order has not very many items anyway. And each item, of course, refers to a single product, right? If you need to find out what normally Alice has bought, so that you can make recommendation, because, oh, okay, Alice usually buy potatoes and dry spaghetti and so on. So when you want to do suggestion or recommendation to Alice, you should suggest something based on her previous history of buying, right? Okay. How would you write the query to return this? Of course, you need 1, 2, 3, 4. 4 tables joining for sure, right? But here, of course, you can, of course, it is a little bit simplified, but you can even make a graph that contain only the product and customer relationship. So If you want to do promotion for potato, you will know for sure that any node that links with potato, they are potential customers. And then the query is simple and easy. Locate first, find or match potato node, and then connect from potato, potential customer. That's it. Then you start doing the promotion with those group of potential customers. Or when a list comes to the shop, instead of asking, do you want Coca-Cola? No, you should ask something that, hey, Alice seems to be interested in spaghetti, right? Do you want spaghetti? We found that you forgot to buy spaghetti this time. Then this remind is helpful to be able to get more purchase, right? Not to randomly suggest something, okay? All right. So when it is relational model, when your data is bigger, the more we go this way, means the size of data grows. Then the time for executing the queries will increase. More or less, if it is relational model, when data is bigger, the time it would take to execute the query would become more. Okay. But with graph, of course, we still graph model also has some limitation in terms of scalability as well. But this has to be trade-off and has to be done well when modeling graph. I found that in many cases, you would find graph performance in terms of query could be slow, but it starts from first, not very good way to model them too. Okay. So actually, data modeling and data design is one of the very starting point to ensure performance and scalability of your system, data intensive system. Okay. And this is an example of some typical complex joins in SQL, in which for the same query, when it is represented and executed using graph, so that is to compare. But of course, there are something in the very same direction as well, that something could be very complicated to do in graph, but better to do in relational or in some other model. So there are situations for every data store, data engine as well. And this one is to find who reports to John in terms of employee and supervisor, boss and subordinate relationship, and count how many of these subordinates John has. And sometimes we also want to make it kind of recursive. Those, suppose John supervised A and A supervised B, B supervised C. By the chain of command, right? John actually supervised all these A, B, C, right? So if you want to include this kind of recursive relationship, it would be very complicated to do in relational model. Not very straightforward way, but in graph, you can do the recursive modeling, querying easily. Okay. maintenance in relational model. That is what we already mentioned. So with the graph, the very first thing is the intuitiveness, as I mentioned, the very straightforward way to understand the data is one of the big advantage that graph has. Okay, the big benefit of graph to model and store data, nodes, and relationships. This is the very key strength of graph. Performance could be another key strength related to graph traversal, relationship traversal. Okay, this is one thing that graph can do very well. The traversal algorithm remains constant. Even the graph itself grows because even your graph is very complicated, very big. I mean, but once you can first identify the starting node, traversing, if the hop of traversing is not very many, then it's finite, right? It does not grow proportionally to the data size. That is the why it is set here. Performance remains constant, even the data grows. Okay. Queries are compact. This is one strong point and readable. Sometimes you find it's very difficult to read relational table and maybe 4 or 5 ways joining, right? Okay, this one join with this, mean this and this. You really need to work hard, right, in your brain. What does it really mean, all those joins? But with graph, you just, okay, follow this. Oh, okay, it means this. Okay, so the model itself is very intuitive. The query itself also the same. Okay, I think that is what else I should say. The schema alteration without migration, that is one thing, as I already mentioned. Sometimes you focus on only this part. So migration and then adding more nodes and so on, that doesn't affect or impact the certain parts of the graph, will make no impact to the whole data store. So migration will not be so painful. Okay, you can migrate certain parts of the graph at a time. That is one of the good things for data migration and data maintenance with graph. Okay, but still, graph has some, of course, pros and cons. When the data itself is so big or small and the relationship size is so big or small, this is the thing you may need to trade off very well. And as I always mention, not every data model and data store is good for everything, right? There is the task, the scenario, the case where this particular model is best. And there are also certain tasks and scenarios where this particular model is worst. Okay, so we need to really choose the right model for the right job. And I think, yes, that's all.